Hello everyone, and today I have the task of waking us up from lunch by talking about VMAS, Vectorized Multi-Agent Simulator for Collective Robot Learning. So what is VMAS? VMAS is an open source simulation framework designed for efficient multi-agent reinforcement learning benchmarking, and it's comprised of mainly two components: a vectorized 2D physics engine using PyTorch and a set of challenging multi-robot scenarios. So but first of all, why do we even need to do learning? Well, it turns out that the centralized sequential decision-making can be extremely hard. And as an example here, we see one problem that we're all familiar with, which is multi-robot path planning. And to solve problems like these, we can go two ways. One way is to use exact methods, which yield us optimal solutions. But the complexity of such methods can scale exponentially in the number of agents. On the other hand, we could think of using heuristics or meta-heuristics, which have good computational complexity, but often lack optimality guarantees. So multi-agent reinforcement learning has recently re-emerged as a technique that can kind of give us a trade-off between these methods by approximating optimal policies through learning, and it can officially generalize to new problem instances. So now that we know why we want to do learning, why another simulator? Every year a new paper comes up claiming to be the last simulator that solves all problems. So we didn't want to introduce yet another one. So we actually went in the literature and we reviewed works coming from two domains, robotics and multi-agent reinforcement learning. And we kind of classified existing simulator according to certain characteristics that were of interest to us. So these two domains have actually focused on different aspects, while robotics focuses more on high-fidelity simulation and low-level details, such as simulating sensors and dynamics. Multi-agent reinforcement learning focuses more on high-level problems, like video game-like scenarios, where we actually, they focus more on the high-level coordination strategies rather than the fidelity. And we kind of want to strike a balance between these two worlds with our simulator. So we can discuss what are these characteristics, but now I will discuss what our VMAS is. So what are the features of VMAS? Well, first of all, there is this word in the title, which is vectorized, and this means that it allows for massively parallel simulation on GPUs. And this is done by leveraging the single instruction multiple data paradigm. We leverage basically simulation in a batch, and this can scale up computational complexity, not only for GPUs, but also for CPUs, thanks to PyTorch implementations. Second, we wanted it to be simple. So there are these full-feature physics engine or video game engine, which present heavy computational burdens. And on the other hand, we want to tune complexity of our simulator according to the need. So if we want to, we can tune basically the level of complexity according to the fidelity we desire. Third, we want it to be general. So we want it to be a platform for implementing general high-level multi-robot problems in 2 dimensions. And one of the core tenets actually is to make it extensible. So it's not only a physics engine and a set of scenarios, but we have actually focused on making the interface for creating new scenarios as intuitive as possible and abstracting out the implementation details so that more scenarios can be created and shared in the community. We also want it to be compatible, of course, so it is out-of-the-box compatible with the more popular training frameworks and interfaces for multi-agent reinforcement learning. Here is an overview of the core, the structure of VMAS. We have these main components: the interface, the core, and the scenario. The interface is what interacts with the outside world, and the core, on the other hand, is where the simulation happens. So the simulation is force-based, so basically the agents are fed the forces and torques as actions, and we resolve all the constraints in the physics through forces. This can be equality constraints, such as collisions, or equality constraints, such as joints and linkages. And also we have other forces, for example, gravity, friction, drag, and so on and so on. And so basically we have elements like agents and landmarks in the simulation with different shapes and different parameters. And lastly, we have the scenario, which is actually the component which defines basically your multi-robot task. And it's going to be implemented by implementing those 4 underlying functions, where main word makes the word, reset word resets the environment, and then the reward function defines what is the task and how we are rewarding the agents. And observation defines the set of sensory input that is given to the agents during the task. And this can be tuned to tune complexity, of course. So how does this fit in a machine learning or reinforcement learning framework, a training pipeline? What does this look like? So basically, in reinforcement learning, we have these policies that represent the controllers of the agents, which interact with the environment, in this case, VMAS. and they collect these triples of actions, rewards, and states. This process is called sampling. So sampling, the samples are then fed to the neural network training, where we compute the reinforcement learning loss using these rollouts, and we actually backpropagate the loss through the neural network policies to improve them. And the new policies are then fed back to the simulators to collect new data. And since the training is performed usually on GPU devices in a batch manner, what VMAS allows to do is actually to use the same devices for simulation as well, and to scale to a massive number of environments seamlessly. So we can use the same infrastructure for all this pipeline and speed up the whole process. So, but what is the impact of this vectorization? So what we do here is we compare with one of the most used benchmarks, which is the OpenAI MP simulator, which was introduced with the paper MEDPG. And basically here we are plotting the number of parallel environments on the x-axis and the execution time on the y-axis. And we can see that for OpenAI MP, which only runs on CPU, the execution time grows linearly in the number of environments. While for VMAS, on the GPU, basically the execution time is not even impacted by the number of environments. This means that we can run 30,000 parallel simulations at the same price of a few hundreds. And even on the CPU, we observe great benefits thanks to the PyTorch implementation. So the CPU is the orange line and the GPU is the green line. Here are some scenarios. In the paper there were 12, now there are more, but basically we also are compatible with all the scenarios in the OpenAI paper, which are not presented here. And these scenarios vary in difficulty based on the information that the agents are allowed to have. And in particular, I want us to focus on the four leftmost scenarios, which are the ones that we actually benchmark in our experiments. And in the weak scenarios, we have multiple agents actually rotating a rod at the desired speed. In the transport scenario, agents have to transport the package to a destination. In the balance scenario, they have to balance a sphere package on top of a rod under gravity. And in the give-way scenario, they have to give way to each other in a narrow corridor. So what we do is that we run four baselines that are all based on variation of the popular machine learning algorithm called PPO, which is a policy gradient algorithm. And basically, these baselines vary in the centralization or decentralization of the actor, which is actually the policy, and the ornithritic, which is the value function. And I'm not going to discuss in detail, but basically what we observe is that different scenarios challenge these algorithms in different ways. For example, the weak scenarios was not able to be solved by any of the algorithms, while the balance was solved by all of them. And this is due, the balance being solved by all the algorithms is due to the fact that there is kind of global information, so they're aware of the relative position to the package, but this will be removed and, for example, substituted by LiDAR observation or something more local to increase the partial observability. So I'm presenting this to a community of roboticists, so the question that comes to mind is, nice and everything, but does it work in the real world? So what we did and what we're showing here is a deployment of a single agent policy, where on the left you see VMAS and on the right you see our robots, and on the left this agent is trained to move in a circular trajectory, and on the right this is deployed on a DJI RoboMaster holonomic vehicle in our lab, and the agent is actually able to track to reproduce the policy as a simulation. And for the multi-agent version of multi-agent example of deployment, here we observe above the simulation in VMAS and underneath the real-world deployment, and this is a task where basically two robots have to swap places, the give-way scenario, and here basically they're observing the relative position and relative velocity to each other, then they're communicating those, in this case using a GNN, in real time, and they're taking the decisions of giving way to each other, etc. So what were the key enablers to this deployment if you want to do the same in your research? So first, what you need to do is to tune the physics simulation to the real-world platform and the environment. Examples of this is friction coefficients or other physics parameters. Here you're seeing a policy of a robot that was trained to go to a fixed point, which I'm actually perturbating by kicking the robot. And basically, you can go back and forth in an iterative process to understand what is the friction coefficient of your robots. And secondly, what we did is that we actually implemented low-level controllers in VMAS. So the standard VMAS simulation uses forces directly outputted from the policy. But in the real-world deployment, what we had is actually that we have a controller that actually takes velocities and outputs forces. So we wanted to actually leverage this controller that we already have. So what we did is that we pre-appended to VMAS this we implemented the PID controller so that the neural networks can focus on learning to output velocities, and we can outsource the complexity of translating those into forces to a first principle method, which is actually very good in doing so. And basically this layer here, where we put the controller, can be used also to introduce motion constraints, for example, differential drive or something else that may mimic the motion model of your robot. So why should you use VMAS? Just as a takeaway points. Well, if you want to benefit from massive parallel simulation thanks to vectorization, and this is not only for learning paradigms, but you could also use it for your research that doesn't involve learning. If you want to implement hard multi-robot or multi-agent problems in a few hours, and if you want to leverage the benchmark of the set of scenarios that we already have, and it's going to be increasing and increasing with the research from our lab. Okay, so this is the last slide I have here. I'm just reporting recently, we just made an update which includes linkages and joints in VMAS. So here are some of the new scenarios that I've been working on, and these come from my research, which is in heterogeneity. So you can see that some of them have some form of heterogeneity inside. And you can scan the QR code, and basically we already have a README with some notebooks, and you can just press play and try to train VMAS on Google Colab CPUs, GPUs. Thank you very much.